work?
Le Châtelier.
Yeah, it works.
Le Châtelier.
That's how you pronounce it. Chatelier or something. Okay. So what's the big deal? We have a can of Diet Coke, Jasmine. Right? You haven't opened it yet. Is it at chemical equilibrium, that can of Coke?
Yes, because it's in a closed system.
In a closed system for sure. Well, maybe not. Maybe not closed because if it can transfer heat. But the question you ask yourself if something's at chemical equilibrium is, are the concentrations of products and reactants changing over time? Are they? It's inside here, inside the can. Are the constant? Anybody? The Coca-Cola manufacturer definitely doesn't want the concentrations of products and reactants changing over time inside its sealed can. That'd be horrible, right? Now, you know after so many years it's supposed to have changed, but that should be really slow to go bad, right? You pop the lid, and then this stuff happens. So is that at chemical equilibrium, Alyssa? All these bubbles are foaming out and coming over the edges. Isn't it changing? It's releasing gas. So something changed, and now it's not at chemical equilibrium anymore. It will be once the bubbles stop. Why weren't the bubbles created inside that can? The can is at a really high what? Pressure. So what changed to go from equilibrium to non-equilibrium? They changed the pressure, right? Yeah, they lowered the pressure. Okay, all those bubbles could actually escape. They use this principle of equilibrium and Le Chatelier's principles all over the place. And it can get really complicated, like with the carbon cycle, or you've heard of the greenhouse effect, right? Which gas are they worried about? Does anybody know? Coming out of your tailpipe. Carbon dioxide. Carbon dioxide, right? That's one they're all worried about. No, a little bit of carbon dioxide, but not much, right? It's all carbon dioxide is a real problem. And what do they say is going on with the planet? Now, the they is pretty much every climatologist on this planet, by the way. But what do they say is going on? Global warming. Things are supposed to be getting hotter, right? Not colder, hotter. So how many degrees are we talking about? I don't know. Just a few degrees, right, over so many years. Okay, but so what would be the solution? If you believe what all these climatologists are saying, and they're all pretty much agreeing on this, what do you have to do? What's that? Plant more trees, that would help, but really pretty much stop outputting what? The carbon dioxide gas, right? Okay. This is where I think the greenhouse effect to me is really worrisome. And the older you get, the more worried you get about things. But this is kind of a biggie because things are warming up. You make the changes right now, right? Right now. I mean, everybody walks. You make huge changes, right? So everything's solar. Go through everything you need to do to stop the CO2 stuff. Would you as a human being notice this on the planet? Would things stop warming up? Would the greenhouse effect stop? It happens slowly. Now, how slowly? Now, carbon dioxide has a molar mass of only 44. It takes a long time to get it out of the air, because that's the issue. You got to get all that CO2 out of the air. It takes over 100 years. So this cycle, I mean, they make the cycle look really nice, right? Ooh, right? This is going to happen like a day or so, right? Sun comes up and no, this is like a 100-year process. So you make the changes now, Yeah, you got to wait 100 years before you see an effect.
But,
So things are going to keep warming up.
but if we don't change it, everything, why does it go faster? Like, you know what I mean?
What do you mean faster?
Because you say that it takes a long time to get rid of carbon dioxide.
Yeah, so how long have we been putting this in the air?
Over 100 years.
Industrial age is pretty much when it started, right? So it's pretty much like a thermostat. That's what this, and it's, I mean, life owes itself, if you follow evolution, owes itself to the greenhouse effect. Because without it, our temperatures would be fluctuating wildly on this planet. But CO2 is like a thermostat. So all we're doing by increasing CO2 is increasing the thermostat. It takes like 100 years to adjust that temperature, but anyway. So Le Chatelier's principle, what is it? So we have a thermochemical equation. We have some reactants, products, and the enthalpy of the reaction. Let's ask Diana, how would we write the Kc expression? Kc would be what over what? Yeah, exactly, but what would you write? Concentration of, good, concentration of D, whoop, all over A and B squared. Okay, so that's our equilibrium constant expression. You divide the concentration of products by the concentration of reactants, and they're not changing over time, and you get some number, K, Kc. And if you don't get that number, if you divide concentration of products by reactants, you don't get that K number, you're not at equilibrium, okay, for this system. So if the above reaction is at equilibrium, what could you do to mess it up? What's something that you could do, Crystal, Zamora, to mess up this equilibrium? What could we do?
Equilibrium is when both they're being changed at the same time, right?
Well,
Reactants, products, it's going back and forth.
yeah,
Right?
you're producing at the same rate, yes. So you can't stop that.
So
Something to mess up this equilibrium. So we're not at
adding a catalyst.
add a catalyst. That's a good one. But if you're at equilibrium, he just lowers the energy of activation. So you're still going to have the same amounts of reactants and products. So add a catalyst is a good trick question for something like this, because there's no effect for add a catalyst. That's a good trick question. So not that one, though.
Adding more
Add more what?
reactant.
Add more reactant. Pick a reactant. Add more A. That messes up your equilibrium. Add more A. Because now your concentration for A is too big. You're not going to get the K anymore. So if you have too much reactant, the system has to respond by getting rid of that reactant. The only way it can is produce some product. That's what it's going to do. It's going to produce product. Okay, what else could you do to mess up this equilibrium? Tegan. Add some A. Add some B. All right. We could add some C. Could we add some C?
Yeah.
Why doesn't C matter? It's a solid. It doesn't show up in here. You can add C, remove C, it doesn't matter. Okay? So that's kind of another trick question. You can remove stuff, right? Remove A, B, or D. That would work too. That would mess up the equilibrium. Okay, how about this temperature and pressure thing? Right? Why not? Change temperature. Increase pressure. Sometimes that works, sometimes it doesn't. So let's put a question mark by it. We're going to have to figure that one out.
So increasing
Okay.
temperature would affect the kilojoules per mole.
Yeah, we could increase temp or decrease temp. So these are all effects that you could do to mess up the equilibrium. So what is the effect on the equilibrium? Does it shift towards products? Does it shift towards reactants when we mess with any of these parameters? Temperature, pressure, amounts of reactants and products. That's what this is all about. So let's take a look at this and see if we can predict it. Okay, so the below reaction's at equilibrium, and we are interested in compound D. When we make each of these changes, will we end up with more or less D through Le Chatelier's principle? Right? Things need to go back to equilibrium. So I don't know, pretend D is super expensive. You just want a lot of it, right? So that could be the whole idea of this. But we're going to remove some A. Erica, we're going to remove some A. So answer to our question is we'll have less D or more D, or there'll be no effect if you remove some A. What would be the effect on D? Would it be more? Less? Or less? So how I look at these things is I don't look at A itself. I look at A and say, is it a reactant or a product? A is a reactant. So if I remove reactant, I don't have enough reactants. So the equilibrium has to shift towards reactants to get some more, right? So I can get back to equilibrium. So if we remove a reactant, it's got to shift. The whole equilibrium has to shift and produce some reactants because you don't have enough anymore. Because remember, K is just products over reactants. That's all it is. So if you don't have enough reactant, you got to get more. So if I'm going to shift in this direction, I'm going to end up having more or less D. Less. No. We'll get to that, but not yet. Okay. Remove some. Okay, we're going to remove some C, Danny. What would be the effect on D if you remove some C? Go with the reactant product idea. If you remove C, now you don't have enough. Well, if you remove C, everything was all hunky-dory. All the amounts, concentrations were perfect for equilibrium, whatever they were. Now we take away C. We don't have enough product anymore. We don't have enough product to get that K number. We don't have enough product. You have to generate more product, so you have to shift towards more D. You have to shift towards products. If you don't have enough product, you got to get more. There's only one way to get more, and that's this whole equilibrium shifts to get back to it. So we'd end up having more D. Okay, this one's a tough one, Vivian. This one is not straightforward. We're going to add an inert gas to increase pressure. So don't worry about this whole inert gas thing. I mean, they could just as well have used a piston or something. The point is they're just increasing the pressure. What creates pressure, Vivian? Solid, liquid, or gases? Gases. Gases generate pressure. So what we're going to do is look and see how many gas molecules are on each side. And the side that has the most gas molecules, he's going to be called the high pressure side or something. How many gas molecules are on the reactant side? 2. How many gas molecules on the product side? 2. So there's no difference. So we can add pressure, we can remove pressure. The system can't respond because they're both balanced in the first place. So we'll have some more practice on this coming up. But
What if it wasn't balanced?
yeah, exactly. Right? You'll see that down here. But let's make one up. Let's make this a 3. So then we have how many gas molecules? 4, right? Right? So did everyone agree you have 4 and 2? Okay, so now we increase the pressure. The pressure is too bloody high. The system has to respond to remove that pressure. So it's not going to shift towards where D is, because if it does, that's generating even more pressure. That's against what nature wants, right? Nature, you increase pressure, the system wants to respond to reduce it. Well, it's not going to respond by creating more pressure. It'll go to the low pressure side. And that's what's going to happen in what's coming up. Okay. Next one is increase the temperature. Okay. Now the trick to this one, Crystal Munoz, is to write the word heat as a reactant or a product. She says it's a reactant. Are you sure? Well, the only way you can tell is by looking at the sign of this delta H. It's negative, so that means it's endo or exo. It's exothermic. And if it's exothermic, heat is where? Product, there you go. Okay, so heat is a product. If you're increasing the temperature, Gabby, we have too much reactant or product? Well, heat is a product. We're increasing the temp, so really we're adding product. So if you have too much product, it has to shift towards reactant, more or less D? Less. So you have less D. Okay, so what we're going to do a little different, we're going to go to the boards and just work out a couple problems, and then we'll come back and do some math. Okay? So let's go to the boards and just write your answers for this stuff and see if we can all agree on it, and then we'll come back and work on some math. So we have a reaction, and we are removing P2O6. And we're interested in oxygen. So pretty much you just say, well, more or less or no effect on the oxygen. So just scribble down your answers and we'll see if everybody agrees. The effect on oxygen, O2, if we remove some diphosphorus pentoxide. What does no mean?
Well, if there's no P on the left side, then it's just going to kind of stay as P2.
So they're taking the amount. So they're removing it. So now you don't have enough reactant anymore.
Wait, they're removing P as a
They're removing this compound.
Oh. Okay.
They're removing that compound, so you don't have enough reactant in E.
Is it always at equilibrium?
At the beginning, yeah.
That's right. Yeah.
And then it has to, you're going to mess with it, and what does it have to do to get back to equilibrium? And that's what you're trying to predict.
So you have, if you remove P2O6,
You don't have enough reactant anymore.
Yeah.
So it has to shift to get some reactants.
But you still have a product.
Yeah, I mean, you will end up with some amount. But the point is how are things going to respond? The system's going to respond by phosphorus and oxygen reacting to make P2O6.
Okay, but if you remove some P,
Yeah, so you're removing it. Remove all of it. Remove some of it. Doesn't matter. The response is the same.
inert gas,
Just increasing the pressure. Inert doesn't mean anything. Just means doesn't react.
How do we do that one? Because on the other one, you know how we counted?
Yeah. Well, try it. See if you can agree with who's writing around you. Someone should argue with you, Crystal. Someone believes strongly in their answer. Gabby looks strong in her answer. At least she wrote something down. So did Danny.
That's why I don't know how to count. If we use, because I don't know if we just use this number, so it'll be 2, 3, that's why.
So we'll wait for everyone to get an answer, then we'll go over them.
Yeah, that's what I'm thinking as well.
See if we all agree.
I'm just trying to get, that,
So this whole thing is just one gap. You just pretty much add up the stoichiometric coefficients. So this is just a 1.
Right.
don't count him, he's a solid. This one has 3.
That's 1 and 3, and we don't count.
Okay, so you're removing some diphosphorus pentoxide. I think most everybody agreed on less, right? Because it's going to shift, it'll shift that way. If we remove some P solid, because it's a solid, so it's kind of a trick question. Right? Trick question. That was a solid. Okay. Now we're going to increase the pressure. What's the effect on oxygen? If you increase the pressure, I hear a lot of people are writing less. Most everyone's got less. Over here you have how many gas molecules? 1. Over here you have 3. So if the pressure is increased, the system has to respond by decreasing it. So if it shifts to where the oxygen is, for every 1 gas molecule, there's now 3. It's creating pressure. It's not going to create more pressure. It has to get rid of it. So it's going to have to go that way. It should be less. If you wrote less, you got it right. Last one is increase the temperature. Less or more O2. I see a lot of more O2s. Good, because you wrote heat over here. So now you have too much reactant. More O2. Okay, one more at the boards, then we'll come back. Just answer this question. Yep. The gas one?
The ratio, the 1 to 3.
Okay. So I think because what generates pressure? Gas molecules do.
Okay.
So if you have, here you have 3 gas molecules, here only you have 1 gas molecule. So if all this reacted and went this way, the pressure would have to go down because now you have 3 gas molecules in comparison to 1. If it goes this way, 1 gas molecule turns into 3, and pressure can't tell. It's just more gas molecules. So if it goes this way, the pressure's going up. And what they did is they made the pressure really, really high. So the system can't tell. It's almost like it believes there's too much of this because the pressure's too high. Because this only has 3 gas molecules, this one has 1. So it's like pretending this side there's too much product.
Okay.
But the system can't tell.
So because there's too much on this side, then we're moving it.
Yeah,
And then we're to get less.
kind of. You can kind of think of it that way. But I think a healthier way is just you have to reduce this stress. You have to get rid of it. The only way to get rid of high pressure is to create lower pressure somehow. And that's one. But however you conceptualize it. So for the answer for 81, you should be writing low temp or high temp, low pressure or high pressure, one of those two. That's what you have to be picking for 81. Low or high. Both temperature and pressure. I guess a third possibility is no effect. Right? That'd be a third possibility. The temperature, you have to write the word heat as either a reactant or a product. Heat's a product because delta H is less than 0. So you have to write the word heat as a product. And that helps you answer the temperature one.
So the temperature is going to be negative. It'll be on the product.
Yeah, so write the word heat on the product side. Good. A lot of folks have seen that delta H is negative, so they're writing heat over here as a product. Okay. So pretty much if you don't know the answer, you just try it and see if it gives the right result. They want NO. They want this guy.
So, or
Let's do the temperature one first. So would you want there to be a lot of heat or a little bit of heat? All right? Because you want to optimize this guy. You want the maximum of them, right? NO? Does everybody agree? So if you want to get the maximum amount of NO, well, you could suck out all the water. That would work. You could add a whole bunch of oxygen. That would work, right? So those are the easy ones. But they're talking about temperature. So is heat a reactant or a product? Heat is a product. So let's just suck it out of there. Make a hole. And then the system has to respond to generate it. So how can you suck up all the heat? Make the temperature really low. Make the temperature very low. Okay. See if you can figure out the pressure one for optimum yield of nitrogen monoxide. Does anyone have a guess? Think it's low? Think it's high? Heard them both. Low. Okay, we want optimum NO. How many gas molecules on the reactant side? 9. How many on the product side? 10. Okay, so we want optimum NO. So which side has a higher pressure? The products. Now, what you can do is try to figure it out that way. I think it's often faster just to make one up. In other words, pick high pressure. It's always easier to add stuff. So let's say we're going to add a whole lot of pressure. I'm not even for sure if it's the right answer. Just say add a whole lot of pressure. Which way would it shift?
To the left.
Yeah, do you agree? So if that's giving you the wrong answer, the answer must be low pressure. To me, that's very often the easiest way to do this stuff. Is just pick one and then see what the effect is. So come on back. And we'll go over one little question quick, and then we'll do some math. So in this diagram, why is this a poor description of equilibrium? I think whether you're answering A or part B, it's just that, what's the D word when you're supposed to be describing equilibria? There's the D. Equilibria are dynamic. You have to be producing reactants and products the whole time. There's no way you can do that with a scale. So it's, in that sense, it's a poor choice. Equilibria are dynamic. Or equilibrium is dynamic. Okay. So I know what's coming up in the upcoming class periods, so I want us to try to reduce the issue of the math. And what I've done is I've thrown the ugliest algebra problems you're going to see. So you're not going to see every possible algebra problem. You're just going to see the ones that I'm showing you. So let's start here. I want to solve for the variable a. What would you do first? Multiply what? C plus D. Exactly. Be really comfortable with that. You see what people are saying? They're comfortable with this. Just move this up to the top. Right? It's that cross multiplying thing. You can always do that. So you'd end up with a plus b, right, equals, I guess you'd have E and F, and the C plus the D. And on the bottom you'd have the G plus the H. So then there'd only be one step left. Jasmine, what would you do now? Solving for A. Subtract b from both sides. Perfect. So you'd have a equals e plus f, c plus d, g plus h. Just subtract b. Right. Okay. All right. So that's our answer for that one. How would you multiply this stuff out? Alyssa, how would you do this?
I would do
The box? So what's the box?
It's from
Yeah, the foil thing, right? Okay, the box, the foil thing.
You could do A times C and A times D, and then
Yes, it's so much easier what she just said. You hear what she said? Just take the A, multiply it through this, take the B, multiply it through that. That's going to be so much easier because you have calculators. So simplify your life using these calculators. So multiply the A through it, multiply the B through it, you're done. So try that. Show me that you can do it, and then we'll go on to the next one. Right? Everyone with me so far? No problemo. Okay. This looks a lot uglier than it actually is. So this is part of the homework that's due for the next class period. But our goal is to write equations that look like this. And A, B, and C are just numbers. Okay, A, B, and C are just numbers. So once you figure out what your little a, once you get in that format, ax squared plus bx plus c equals 0. Once you get in that format, then you know what your little a, b, and c numbers are, and you substitute them right into here, and you'll get two answers. Why do you get two answers? There's a plus or minus thing up there. Right. So in all these, that's why there's two answers for all these questions. Okay? So here's our expression. We need to get it in the format of ax squared plus bx plus c equals 0. So what would you do first, Diana? What would you do first to get it there? Yeah, we want to do that, but you have to rearrange this. What would you rearrange first? Cross multiply, right? This thing. Be really comfortable with just moving stuff around from one side to the other. It doesn't matter what it is. You can do that. So how does that relate to this? Move the 500? The 0.5 minus x, just move it up with the 500. Because then everything's up on top. And that's the big goal. Move the 0.5 minus x up there with the 500. Right? So you'd end up with 500 times 0.5 minus x equals 2x quantity squared. Okay. Now what would you do, Crystal Zamora?
so is it 500? I'm confused because we're supposed to get it to look like the ax squared.
Yeah. So we gotta multiply all this stuff out.
Okay, so like
Distribute that 500. Right. So 500 times a half is 250 minus 500x. That has to equal, well, we could instead, let's call it 4x squared. Okay. Now you have two choices, right? We can bring the 4x squared over here, or we could bring all this stuff over here. Either way, it will work. You have a calculator. Either way is perfectly fine. You can get the exact same answers. I just know folks who have done this before, for some reason, they don't like to have their little a's, whatever's in front of the x squared, they don't like it to be negative. It doesn't hurt anything. but that's fine. Let's just keep it positive because a lot of most folks are used to it that way. And I guess if it is negative, you have a little extra plugging in the calculator, so there might be an advantage. I don't know. But let's just bring this stuff over there so we can keep our A positive. So you'd end up with 0 equals Tegan. What would you get? 0 equals?
4x squared plus 500x minus 250.
Perfect. Okay. Now, what is my little A, B, and C here, Jarixa? All right. We have it in the right format. What's my little A?
4x squared.
Just the
4.
just the 4. And my little B? Sorry, that's A.
500.
500. And my C. Yeah, is it negative 250 or positive 250?
Negative 250.
It's negative 250. It's the whole thing. Okay, so plug those things into our little formula up here, and you should get 2 answers, and they're written up there. Now, when you square something, just use the x squared button. It's easier. So when I do this, I would do the part inside the square root first, right? So 500 and square it. And then I can notice I can cancel my minus signs or just keep them in. Either way will work. Okay, now do the rest. If I just write out some intermediate steps here so you can follow it on your calculator. I've got 254,000 inside the square root. And to take the square root, I have to do the shift. So make sure you get those 2 answers. Get it to work on that calculator.
What's the best way to do what's inside the square root?
Okay. What I think the best way is not to just know how to use the calculator completely. So let me do it this way. Let's do the 500. Do it together. 500 squared, the x squared button. Okay. And then it says minus, so let's do minus. Minus 4 times 4 times 250, but then push the little plus minus guy to make it negative and hit equals 254,000. And then to take the square root of it, shift square root. Okay. So if you got these 2, try to set up the next one. And this equation 2 is as ugly as it can possibly get. It can't really get any worse than that one. Yep. Yes, this works. But it doesn't really help you because you have to get it in this format. So you still got to multiply the whole thing out. but that works. So when you start with this next equation, you have several choices. One is you could take the 0.1 through and the negative x through and do all that, then move it all up there with the 50, and then multiply through that whole 50, right? So there's different ways to approach this one. Some quicker than others, but it's good practice. I don't know if you noticed, but even the one we just did, you could have divided through by 4 in this whole thing. It wouldn't change your answers at all. Okay. So work on this. Come by. I'll be glad to help you out, especially in lab. Just come by. Got a lot of time. I'm just sitting around in lab.